When I find myself moving too fast through life, oftentimes I realize it's because I'm wired on way too many Red Bull energy beverages. When your data is moving really fast through a network, it is often moving through a wired topology. In this, we're going to take a look at some examples of wired topologies, and we're also going to make sure we understand the difference between a logical topology and a physical topology in the network. When we think about a logical wired topology, we think about an abstraction of how the communications are taking place. For example, a user here on computer 2 wants to access their Dropbox, which is located out on the internet. For them, the logical topology is their computer, the internet itself, and then their Dropbox located in the internet. So they're really abstracting what is going on with the logical topology. They think, all right, all I need to do is use my computer to connect to the internet to access my Dropbox. But if we were to look at the physical topology, we would see that it's much more complex than that. Sure, it involves computer 2, but it involves then switch 2, router 1, the firewall, router 2, the service provider, and then the facilities up at Dropbox. So we love logical topologies, and we do them in varying degrees of detail so that we can get a look from a bird's eye view, if you will, of how information or data is flowing through the network. But when it comes to really precise troubleshooting and even tracking down maybe a bottleneck in the network, it is often critical to also look at the detailed physical topology. Now, you won't be surprised to learn because there are so many different networking technologies, there are many different possible wired topologies that we could utilize. An early type of topology is called the bus topology, and notice your network nodes are all connecting to this single run of cable. The bus topology was great because it was simple to implement. You didn't need additional devices other than to make sure that each end of this long bus has termination points so the signal doesn't just bounce around endlessly. Now, something else about wired topologies is that every type of topology is going to have some big weakness, and a clear weakness with a topology like this is that a break in the cable would either bring down the entire topology or it would cleave it in two, where you would have two networks now that are not connected. Our next topology is certainly aptly named. It's the ring topology. Similar to the bus topology, you would have issues if there were a break in this cable. One of the things that was designed was a dual ring type of infrastructure where you could have another ring that could be failed over from the main ring in the event of problems with the main ring. Ring topologies tend to be much faster than their bus topology counterparts. One of the most common wired topologies found today is the star topology. In fact, this started years ago when a hub would be introduced into local area networks. This hub would be the central point in a star connectivity. And of course, we know hubs have kind of gone the way of the unfortunate dodo bird, and they have been replaced with switching technology. But even though the central device is now a switch, it is still technically a star wired topology. In fact, the really most common thing we see today is these central points being connected to each other and forming additional stars. So we tend to call a LAN with switches today an extended star network. Now, remember at the beginning of this nugget when we were talking about the logical topology versus the physical topology? Well, that really does come into play with these wired topology examples I'm giving you. Let's go in the way back machine, and there you can see we have a token ring network. What's interesting is when you look at this, you see that the physical topology is actually one of these extended stars, but what is the logical topology? It's two rings. This operates in a ring type of logical topology, and this area would operate in a ring type of logical topology. So keep that in mind too, that there is going to be this concept of a physical extended star in the case of token ring with a logical ring type topology. What about connecting every single node to every other node? Well, when you do this, you have a bit of a mess, but also we like to call it a mesh. In fact, if every node truly connects to every other node, we have what we term a full mesh. And if we don't do it that way, we have what we call a partial mesh topology. So you can play a balancing act with a partial mesh. You can say, I want some redundancy of paths, I want some resiliency in the topology, but I don't want to spend all that money and have the complexity of a full mesh. So the partial mesh becomes very, very common in wired topologies today. If you look at wired topology options, there are so many of them, aren't there? We know there's things like a bus or a ring or a star or even an extended star topology. There's varieties of mesh topologies in the wired infrastructure. With wireless, the great news is it's a bit simpler. There are three main wireless topologies that we need to look at. The first that we will discuss is certainly the simplest, and guess what? It's also the most rare. You can do what's called an ad hoc wireless topology, and you can have two nodes communicate using their wireless directly with each other. This is not really all that common because, for one thing, we have to make sure we rely on the configuration of the two devices from a security perspective. So this would be a temporary solution in order to transfer files maybe between two devices, but it would be something that you would not want to do long-standing because of the terrible, terrible security implications that could go with this. You might occasionally see an ad hoc network referred to as an IBSS. That's an independent basic service set. And the key word there is independent. There is no device that is controlling these wireless communications. You can configure ad hoc connections with your Windows devices, but it depends on what operating system you have, just how easy that's going to be. In Windows 7, for example, it's quite easy. In Windows 10, you have to jump through some hoops and even use the command line in order to do it. On a Mac system, it's actually very simple. You would go up to your wireless indicator here up in your status bar, and then you would just go down to Create Network. And notice I can easily create a computer-to-computer network using the wireless just by giving a network name and choosing a wireless channel. So the most common wireless topology that we are used to dealing with is infrastructure mode. And with infrastructure mode, we have a device, often termed an access point, that is providing the wireless cell that we are going to join with our end node device. The official terminology for the infrastructure mode topology is called BSS, a basic service set. Notice we drop the independent I that we had in the ad hoc network. And our third type of wireless topology is one I bet you've experienced if you've been in an area that has a large size relative to like a small office, home office. So maybe you're in an airport or you're in a park or you're even in a city that provides wireless connectivity wherever you go. This is almost always going to be implemented in a wireless mesh type of topology where you have many access points located in the topology and they are providing the wireless connectivity. Oftentimes, you'll have a wireless controller in this mesh network that is sending the appropriate instructions to the access points. In fact, when you have an access point in your small office, home office in an infrastructure type of topology, we call that access point an autonomous access point because it can act on its own to manage the wireless. In a mesh network, with a controller example like we're giving here, the access points are most likely going to be what we call lightweight access points. They don't have the autonomous behavior we find in the infrastructure mode. They are just following the instructions given by the controller that's on the network. The official terminology that you might see assigned to this type of a network, the mesh network for wireless, is the extended service set or ESS design. These days, there are so many different types of networking technologies, we need some common language to describe networks. So when we're talking to, let's say, another engineer that's supporting us, we can use a common language. One of the ways that we can describe types of networks is to use geography, the overall size of the network, as a descriptive term. In this, you and I are going to take a look at a lot of different options for describing a network type. So here are just some of the types of networks that we can describe, and I've tried to organize these pretty much from the smallest to the largest. So we begin with the personal area network. If we look at this computer right here, computer 2, it might be connected to many different devices that are all in the same room with that device. It's certainly not Peter Pan's magic that's making this happen, but this PAN is called a personal area network, and one of the key technologies that makes it a reality is Bluetooth. Here I am in the Windows 10 settings, and if you go in there and choose devices, notice one of the categories is for Bluetooth and other devices, and you can see all of the different devices from just the mouse, keyboard, and pen perspective that I am networking with. And one of the issues with Bluetooth that we have is it has distance limitations. So by the very nature of that technology, all of these devices are in the same room with me. If I took this Logitech unifying receiver and put it in another office several rows down here in the hallway, then I would lose connectivity with that personal area network device. Now, a larger type of network is a local area network, and I'm circling the local area network that is shown in this network diagram. Notice with the local area network, we're going to have routers and switches making the connectivity possible, and also notice with the local area network, it can connect to a much larger network potentially. So here, the local area network is going to feature common network devices and technology, and it's going to be connected by what we call network media. And today, the most common method of connecting devices in the LAN is to use Ethernet. And we use unshielded twisted pair type of Ethernet of different categories to provide different speeds to the local area network. Now, a local area network doesn't have to be Ethernet, but that is the most common type today. Now, perhaps this organization shown starts doing a lot with media files, specifically videos, like CBT Nuggets does. Well, they might go ahead and they might organize another type of network with its own network devices. They might make it accessible off the router, and this network is really there to do one thing, and that's store these media files and make sure they're readily available when people want them at a high rate of speed. And this is what we call the storage area network, or SAN. We have classes here at CBT Nuggets, as you might guess, that are centered around storage area networking. Notice another type of technology that could be used to describe a network is this access point right here sending out a wireless signal, and this computer 3 way out in maybe a nice little foyer area in the organization, or maybe even outside the organization's main building, is accessing network resources thanks to the wireless, and we like to refer to this as a wireless local area network. Now, here we start getting into larger geographical areas. We have a campus area network, which might cover a bunch of buildings that are located at maybe even like a university campus and connecting them together. A metropolitan area network that might use a media like Metro Ethernet in order to connect a bunch of buildings that are all downtown in a major city. And then we have the wide area networking, which is the ability to connect to resources potentially all over the world, giving us the largest possible network. The largest example of a wide area network is indeed the internet itself. Yeah, your public internet is a massive wide area network that covers the entire globe. And you might think I'm being a bit exaggerative when I say cover the entire globe, but that's exactly what companies like Facebook and Google are striving to do. They're implementing balloon type of technology, as you can see here. And Gosh, the balloon looks so sad, doesn't it? But these types of technologies are designed to spread the reach of that wide area network, the internet, so that they can gain more and more customers to their services. And before we wrap this nugget up, just one more really quick point. We mentioned that there's a type of network called the campus area network, and I want you to realize that you can connect a campus area network pretty easily to another campus area network. And when you do this, you of course have the can-can, a famous dance in which the dancers kick their legs up really high. Decades ago, when I was working in networking, we started to hear more and more about IPv6 and how the address space that would be available to us would expand mind-bendingly. Just an amazing number of available addresses to assign. And it got everyone to thinking at the time, why would we need so many addresses? We were aware that we were running out of IPv4 addresses, but why would we need so many with IPv6? And then really the case was made that in the future, so many more devices would begin connecting to the internet and need addressing. Inside of just a single device, we might have an entire subnet worth of addresses for different components in that device. Today, with more and more things connecting to the internet, we have terminology for this called IoT, the Internet of Things. In fact, some people now are realizing that it should go beyond that terminology to the Internet of Everything, or IoE. In fact, if you're like me, you may be experiencing the Internet of Things right in your own home now. Let me demonstrate.
Alexa, lights 100%.
Okay.
Alexa, lights off.
Okay.
Alexa, ask ADT, arm alarm.
Okay, I armed the system. Stay.
Alexa, ask ADT, disarm alarm.
What is the pin?
And you will note the demonstration terminated abruptly there as I realized I was going to have to say my PIN code in a video that is being distributed around the world. But you get the idea. There is Amazon Alexa working in conjunction with the Hue lighting system and the ADT security system in my home. We start to see everything connected, everything easily controlled, and this is all made possible by an architecture that many Internet of Things is going to follow these days. And what's fascinating about this is these pieces right here of the architecture, they're pretty standard now for much of what we're doing when it comes to networking. It's this piece right here where we see the real inventive stuff. In the case of just the Hue lights that I was controlling with the Alexa app, realize that there's a technology that's been created called Zigbee. And the Hue lights use this Zigbee technology in order for the lights to form a mesh network and be able to exchange messages with each other and extend that network out further as we add more and more Hue lights to the system. So the newer technologies are the embedded technologies, of which Zigbee would be an example. But then as we move up the architectural stack, this stuff has been around now for quite some time and we've been using it. For instance, in the edge, I have a wireless access point, and this has a connection up to the core networking components of my internet service provider, and they're working to give connectivity into the cloud so that these applications can be developed and distributed and even maintained for the Hue lighting system and for the Amazon Alexa device. So not much has to be re-engineered over the cloud technologies that we've been relying on now for the better part of a decade to make software as a service and infrastructure as a service a reality. And I'd like you to keep in mind that my demonstration of the Internet of Things just really scratches the surface. I mean, look at these investment numbers from back in 2015 that the IDC gave us. These are investments in millions in various areas and segments. Look at healthcare and logistics and retail and manufacturing, both discrete and process manufacturing, wholesale, utilities. The explosion in the Internet of Things comes from the enhanced services that can be provided, but also incredible savings and making the planet greener. Think about my Hue lighting system and my ability to set the lights to just 20% when I only need 20% lighting in my home. That's saving electricity in a big way, in addition to letting me set the mood. In this note, you and I are going to take a look at some IoT technologies. That's the Internet of Things. It's here, it's exciting, and let's see some of the underlying tech that can make it work. We know that the IoT is built on tried and true technologies as far as edge networking and core networking and cloud technologies go, but there are these embedded systems and some of them are pretty new. One that we looked at was Zigbee. What a great name. I'll just put ZB to remind ourselves of the Zigbee technology that we might find in something like the Hue lighting system. Well, there's many other options when it comes to these devices being able to communicate with themselves or even a centralized bridge. And some of these you see listed here are no surprise to us, or at least they may be surprising that they're used in IoT, but they're tried and true technologies that we're familiar with, like 802.11. You know, the wireless technology that we've been dealing with 802.11g and 802.11n and 802.11ac. Of course, many devices will leverage wireless tech in order to communicate from an IoT perspective. And then there's Bluetooth with our personal area networking. We could use Bluetooth for one device to communicate information to another device. And then let's go old school for a moment with infrared. Remember your old television remote? In fact, I still have an old school television remote that uses infrared technology in order to communicate information from the remote to the TV, and it's really annoying, and that's why we don't see it all that much in IoT, because it's line of sight. Hold your hand over the little light that shines red at the end of the remote, and you won't be able to change the station. There's near field communication technology. We see this in things like Apple and Google Pay products, where you can hold your iPhone or your Android phone next to the cash register when you're checking out, and there's a little NFC receiver there that will allow you to pay. There's asset tag type technology called RFID, that we can have little chips inside of objects, or maybe even a sticker you place on your laptop so that you can then track that device. This certainly has IoT implications, especially in the fields of like manufacturing. But then we're having brand new technologies created, oftentimes by like a consortium of people. For instance, there's a technology called Z-Wave that's often seen with home automation, and Cisco Systems and some of the other big giants in the industry joined the consortium for Z-Wave, and they put money behind it to help develop the technology. Another example of that is the greatest name in all of networking, Ant Plus. In fact, I'm going to ask that my friends and family start simply referring to me as Ant Plus. Maybe it'll be my network rapper name. Yo, I'm Ant Plus. Ant Plus was initially developed by Garmin, the GPS company. And what that technology does in an IoT sense is it's used in monitoring sensors. This could be something as critical as like a heart rate monitor, or it could be monitoring the tire pressure. I guess that can be pretty critical too for large industrial trucks and things of that nature. So the embedded systems technology note can leverage tried and true existing technologies, or new technologies can be created like Z-Wave or Ant Plus. Be ready to see more Internet of Things technologies on the rise, and the great news is they all have similarities. For instance, if you look at Z-Wave and you were to compare it to Zigbee, the underlying methods and protocol structures are going to be very similar. All of the IoT manufacturers always try and adhere to open standards whenever possible. So you are going to see that while they may develop some new tech in order for the devices to communicate, the devices will be actually transferring messages many times using open standard application programming interfaces or APIs. I hope this has been informative for you, and I'd like to thank you for viewing.
Thanks for watching our second and press the button below, like, subscribe, and bell icon.